Hello dear friends, welcome to a lecture on ring theory. In this lecture we shall study prime elements and irreducible elements in an integral domain. Earlier we have studied prime element in Euclidean ring, but now also we shall consider or study irreducible element and the relation between prime element and irreducible element in an integral domain. I have written here definition of both prime element and irreducible element. In Euclidean ring it is the same, prime and irreducible is the same, but in integral domain this may be different. First we shall see the definition. A non-zero element P of an integral domain R with unity is called a prime element, or a non-zero element P is called a prime element if first condition is it is not a unit. Unit we have defined, unit is the element which is invertible with respect to multiplication, or which has multiplicative inverse. It is not a unit. And second thing is, if P divides A into B, then P divides A or P divides B. P must divide one of them for A, B in R. So this is the definition for prime element. It is not unit, and if P divides A into B, then P divides A or P divides B. Second definition is for irreducible element. A non-zero element A of an integral domain R with unity is called an irreducible element if the first condition is the same again, it is not a unit. And the second condition is slightly different here. If A is equal to B into C, B, C are in R, then either B or C is a unit. If A is written as B into C, then one of this must be a unit. Then we say A is irreducible. Now in the ring of integers with addition and multiplication operation, prime element and irreducible element are the same. But in general, the relation is like this. So prime elements we know for ring of integers, say 2, 3, then 5, 7, etc. are prime elements, or we can consider these as with positive and negative signs. These are prime elements because this satisfies these prime elements as well as these are irreducible elements. But now the general relation between these is written as a result. Every prime element is an irreducible element, means prime implies irreducible, but an irreducible element need not be a prime. That we shall prove. The proof for this. Let us consider P be a prime element of an integral domain R. Let P be a prime element. And we now want to prove P is irreducible. That means if we can write P as B into C, so it is prime means it is not unit. That is the same condition. And now only we need to prove the second. If P is equal to B into C, then either B or C is a unit. That we shall prove. Let P is equal to B into C, where B, C belongs to R. So this is the case. Now P is prime. P is prime and P is equal to BC. P divides B into C. P divides P. That is obvious or trivial. And P divides P means P divides BC. And P is prime. Then by definition of prime, You see, P divides AB, then P divides A or P divides B. Here instead of AB we have written B into C. Then P divides B or P divides C. There are two cases. Now the first case we shall consider. First, if P divides B, then by the definition of divisibility, B is multiple of P, then B is equal to some xp for some x belongs to R. So this is by the relation of divisibility. B is multiple of P. But now from 1, P is B into C and B is x into P. So B is x into P into C. We have written B as xp. And thus what we have is P is equal to xpc. Now from this relation, because it is an integral domain, cancellation law holds and we can cancel P. So cancelling P, or by cancellation law, so what we shall get is 1 is equal to x into C. And what this says, x is a unit, C is a unit, or that means C is a unit. Therefore, C is a unit. Unit in R. This is one case. Now, second case is P divides C. If P divides C, then C is also multiple of P. Then C is equal to some yp for some y belongs to R. And again from 1 that we have is P is equal to BC. P is equal to B into C. Now C is Y into P. So this will be B, Y, P. And again from this relation we can cancel P and we get 1 here and we get BY on right side. So by cancellation law holds in integral domain. What we shall get is 1 is equal to BY. And what this gives, B is a unit. Both Y and B are unit, but we shall consider one part of that. B is a unit. So therefore, B is a unit in R. And thus, considering P is equal to B into C, we have either C is a unit in R or second case B is a unit in R. And that means here you see B is either B or C is a unit, then this product of B into C is irreducible. So this is what proves that P is irreducible. Thus P is equal to B into C implies then either B or C is a unit, and therefore P is irreducible, and that means a prime element is always irreducible. P is an irreducible element. So this is the first part we have proved. Every prime is irreducible. Now the second converse part is not true, that we shall have to prove. Irreducible element need not be a prime. that we will consider as a second part, converse part. To prove that converse part means irreducible element need not be a prime. Now consider the integral domain. We shall have a counter example. We shall prove this result by a counter example. We prove an irreducible element need not be a prime. Prove it by taking a counter example. Let or consider the integral domain. Z under root minus 3. The meaning of this is the elements of this type a plus b under root minus 3, where a, b belongs to z, the integers, set of integers. Z is integers. And all the elements of this type are, and this forms an integral domain. So we consider an example of integral domain. Now we will have an irreducible element, and 7 is the element of this this integral domain. Now 7, or take this element 7. 7 is element of this, because 7 can be written as 7 plus 0 under root minus 3. This belongs to the integral domain z of under root minus 3. This is an element of this. This is irreducible, we shall prove. 7 is irreducible. How to prove 7 is irreducible, that we shall see first. Now in this integral domain, it is integral domain commutative with unity. What is unit element in this integral domain? Unit element or unity is 1. 1, or which can also be written as 1 plus 0 under root minus 3, is the unit element. Unit element of this integral domain. And the unit of this integral domain is 1. This is unit element, it is also a unit, and another unit is there, that is negative 1. Also, now I shall write here, we have to prove it is not a prime. See, the unit of this ring are 1 and minus 1. Minus 1 is equal to minus 1 plus 0 into root of minus 3 is, this belongs to the integral domain, this integral domain. And this is unit of this integral domain, because its inverse is itself. The product of this with itself, negative 1 into negative 1 is 1, and therefore it is unit element. And thus unit element, unit R, Thus there are two units. That is 1 and -1 in this integral domain. Now 7 can be written as 7 can only be written as seven is equal to, see, 1 plus 0 into root of -3, that is 1, into 7 plus 0 into root of -3, or it can be written as -1 plus 0 under root -3 minus 7 plus 0 under root -3. So 7 can be written in one of these form. And now you see 7 is written as A into B. Here also A into B, or another element C into D. Then in this expression this is a unit, and in second expression this is a unit. Means if A is written as B into C, then either B or C is a unit. So this is commutative. Maybe we may write this as first and this as second here also, and but one must be unit. So 7 is written in this form, and therefore 7 is irreducible element, and thus where or 7 is equal to AB, then either A or B is a unit, in this integral domain. See, here these are the units, and therefore 7 is irreducible. This is what we have proved. 7 is irreducible. Now what we shall prove is counter example, 7 is not prime. Second thing, seven is not a prime element of this integral domain. See, we can write or we have 2 plus of minus 2 plus under root of -3. This belongs to the integral domain z under root -3. 2 minus under root -3. This is also an element of this ring integral domain. And what is product of these two elements? 2 plus under root -3, 2 minus under root -3. This is equal to, this is just of the type A plus B, A minus B, and the product is A square minus B square. So it is 2 square minus square of under root -3, that is -3. Or this is 4 plus 3, which is 7. So 7 is written as product of these two, and that means 7 divides this product. Therefore Therefore 7 divides 2 plus under root minus 3, 2 minus under root minus 3. But 7 does not divide any of these factor. But 7 does not divide 2 plus root of minus 3, and 7 does not divide 2 minus under root minus 3. And this does not satisfy the definition for prime element. 7 is not a unit, but if P divides AB, then P must divide A, or P must divide B. This is the condition for prime element, and this condition is not satisfied by 7 in this integral domain, and therefore 7 is not a prime. Thus 7 is not a prime in this integral domain Z of under root minus 3. It is prime in the integral domain of integers, but it is not prime in this integral domain Z negative root 3. And that means a result that we have proved is prime implies irreducible. Every prime element is irreducible, but every irreducible element is not a prime element. So this is the relation between prime and irreducible element. One more thing we shall define is irreducibility in polynomials. Irreducible polynomials. I shall write as a definition. A polynomial P of x belongs to f of x, where f is a field. Is said to be irreducible if whenever we can write P of x is equal to A of x into B of x, product of these two polynomials, where A of x, B of x belongs to f of x, then either A of x or B of x has degree 0. That is a constant. Then that polynomial is said to be irreducible. If the polynomial is written as ax into bx, then one of this must be a constant. Degree 0, polynomial of degree 0 is constant, and then it is said to be irreducible. So that irreducible depends on, see, it is easy to verify that, see, x square minus 5x plus 6. This polynomial is not irreducible because we can write it, its factors as x minus 2, x minus 3, and therefore this is reducible. But if you can write this as in the ring of integers or in the field of real numbers, this is reducible. But if you can write x square plus 1, then this cannot be factored into lower degrees like this in the field of real numbers, but it can be factored in the field of complex numbers, and that we can write as a remark. Irreducibility depends on the field. For example, see the polynomial x square plus 1 is irreducible. Over the field of real numbers. But it is reducible over the field of complex numbers. Since we can write x square plus 1 is equal to x plus I into x minus I. These are the factors possible in the field of complex numbers, where I is under root of minus 1, imaginary number. But we cannot factorize this x square plus 1 in real numbers, and we can factorize it in this form. So irreducibility depends on the field under consideration. So this is the meaning of irreducible polynomial. So thus we have seen what is the relation between prime elements and irreducible elements, and also we have defined what is irreducible polynomial. I hope you will understand this lecture. Thank you for watching the lecture.